Okay, so it is Thursday, September 24th, and this is Psych 522. And today's class is really important because we're going to talk about discriminant analysis. We're also going to talk about the KNN approach a little bit. And then we're going to talk about the multivariate analysis of variance. Now, it needs to be said from the start that our book, James, focuses on discriminant analysis. So the context here is really important. All of their discussion of what we're going to talk about is centered around discriminant analysis and classification. However, as we were talking about at the end of last class, there's a reverse side to discriminant analysis, and that's multivariate analysis of variance. So the big picture of today is going to be that discriminant analysis and multivariate analysis of variance are actually very similar, but they're used for different purposes. Okay, so half of what we're going to do today is look at discriminant analysis as presented in James, and then we're going to flip things around, and we're going to talk about the multivariate analysis of variance as talked about in Stevens. And there's things in James that aren't mentioned in Stevens, so we're merging the two books a little bit as we talk about this topic here. And you'll see why as we go. Okay, so first let's start off with the James presentation. And before we talk about discriminant analysis, we want to talk a little bit about this KNN approach. So in a previous chapter, we kind of glossed over that a little bit. When we were talking about like linear regression, we got to this part where you could have this non-parametric approach, and we could use it for classification. So with the things we're dealing with today is instead of predicting a continuous response on Y, right, instead of this being continuous, well, it's going to be like a 0, 1. And that's what we ended off last time when we were talking about logistic regression. And logistic regression was one way of modeling a binary response. And this one is going to be continuous over here. Well, we look at different ways of working with this data when you have a classification problem. And the first way is the KNN approach. So what is the KNN approach? Well, the KNN approach relies on something called the Bayes classifier. Now, what's the Bayes classifier? Well, we know what Bayes is. Okay, we've looked at Bayes' theorem. We had to look at it in the first exercise. So what does Bayes' classifier actually say? It says that it's going to pick the probability for the given class of Y, so the particular class is equal to J, given a particular value of X. So imagine you have values of X here, and there's X sub naught, so there's one particular value. What the Bayes classifier says is if you put this value, okay, this value of X, what the Bayes classifier is going to do is predict group membership, so the class, for which is the highest probability given, that's the conditional, given X sub naught. So given this, which class has the highest probability? And that's the essential job of these classification methods. They're trying to get you the best group out of what you provide it with data. That's not unlike what linear regression actually tries to do in a sense, right? Because linear regression, instead of this being binary, it's continuous. So you can almost think of it as analogous, where given a particular X value, so given a particular age, while it's trying to predict which group you're in. It's just that the number of groups are very, very large. So in this particular situation that we're dealing with here, we have a grouping structure that is 0, 1. And as we talked about, using continuous linear regression isn't really appropriate for problems like this. That's why we have to move to a different procedure. Logistic regression was one, but the KNN approach is another. So this is the Bayes classifier. The Bayes classifier, what's important about that is it provides the best classification. Okay, in other words, it provides the lowest error rate. So what's the lowest error rate? Well, if I take the probability of y is equal to a particular class given x, so given x, now x could be x sub naught, it could be x sub 1, x sub 2, whatever value of x. So this is a general statement for x that we're using here. The error rate is 1 minus the overall average of that maximum probability of membership. Okay, so you look at this and you say, well, given an x sub naught, I'm going to predict with the highest probability. That's what I'm trying to do. Well, the error rate is 1 minus that overall expectation. So when we think of expectations, when we think about expectations as kind of like averaging over. So 1 minus the overall average given different values of x. That's what that's saying over there. Bayes classifier is number 1. Okay, first choice. That's the first choice. If we could do everything with the Bayes classifier in terms of prediction for these types of problems, we would. So that's number 1 choice. The problem is that you're unable to compute these things with the Bayes classifier because you don't have the information available. So it's kind of like a theoretical ideal because you don't have the densities of y given x. You just don't have those. So you can't read off those probabilities because you don't have that with real data. With simulated data, okay, so simulated data from a computer, we can show the Bayes classifier boundary, but this is entirely theoretical. Okay, this is entirely theoretical. You can't have this with real data. And this is what this is showing is trying to establish a boundary here for a classification that would result in this idea here and having the lowest error rate possible. This is that theoretical boundary over here. But you can see that we've got some overlap, right? We have some orange points over here. We have some blue points over here. So even in this particular case, the error rate is not going to be perfect, right? The error rate's not going to be perfect, but that's the ideal. So we start off with this idea of the ideal, and then we move towards a practical case where we can't use this. But remember, the Bayes classifier is what we'd actually like to achieve. So in these simulated data approaches, what the authors do is they sometimes just compare it to what the Bayes classifier would give you in order to evaluate the goodness of the classification method. So what is the KNN approach? Nearest neighbors. Well, by the words of it, nearest neighbors, you can kind of see how the method is going to work. It's going to look for nearby points, and it's going to say, okay, what's the group membership of those nearby points? So imagine we want to know which group this particular point belongs in. Okay, so that's the point I want to know. Where does that belong? And does this belong in the orange? Does it belong in the purple? Well, look how simple KNN is. KNN says who's around it. Right? It just says who's around that particular point. So it counts the number of points around it. If you specify k is equal to 3, okay, so let's say k is equal to 3, it's looking at those 3 points around it, and what's it saying? Well, it's saying there's 2 blue and there's 1 orange. So it's going to say, well, I'm going to predict that you are in the blue group. And that's exactly what this is saying up here. So here's our conditional probability of y into a particular group. So here there's 2 classes, orange versus purple, for a particular value of x. So give a particular value of x, what's the predicted membership? Well, this is an indicator function here. So this could be, in this case, blue, or not blue, purple or orange. And it's going to predict, in this case, that it's equal to the purple group because you have a total of 3 points that we're looking at. And there's going to be 2 over here that are in the purple group. So it's evaluating that probability just by the nearest neighbor idea. Very, very simple approach. And it actually can work pretty good for some problems. And that's what people say about the KNN approaches. They say that's a pretty kind of a crude approach, but for some classification problems, when you try it out, it actually works out pretty good. So, you want to think about it in the spirit of the times that we're in. What's an example of where you might want to use a KNN approach? Well, think of COVID. I mean, think of contact tracing. It kind of makes sense that if you're trying to predict whether this person is in the COVID yes, right, COVID yes versus COVID no group, well, what might you do? Well, I think that's how they do the evaluation pretty much. If they want to know if you're at risk, they give you a test, but before they do that, they do the contact tracing. Who have you been around? In other words, who are your nearest neighbors? And that's exactly what this method's trying to do. So imagine them trying to evaluate the probability of you having COVID by saying, well, how many of your family members have COVID or have symptoms of COVID? Well, 2 of them, and the other one doesn't. So maybe it's going to classify you into the group that has COVID. Okay, that's one way of looking at that. Okay, if we look at increasing the number k here, so this is k is equal to 10 in this particular case. The black curve indicates the KNN decision boundary on the data in figure 2.13 using k equals to 10. And the Bayes decision boundary is shown as a purple dashed line. So in this case, they're actually very similar. I think if you check it out in the book, the error rates are actually, they're actually very, very low. And the KNN is actually approximating the Bayes decision boundary actually pretty well here. Okay. So you can adjust the number of k, and we're going to see over here kind of what happens with that adjustment. Now, what number of k to use? Well, you can try out different numbers. And you can also see that, I mean, there could be potential problems with this too, because maybe you're trying to predict this, you have an orange one and an orange one, but then you have all blue over here. So if it's just looking at a low number of neighbors, maybe it's going to predict you're in the orange group, when really maybe you should be in the blue group. So you can see it's not a perfect method by any means, but in many cases it gets the job done. So you can adjust your number of k. Now if we look over here, let's look at adjusting k equals 1 versus k is equal to 100. So just look at that k is equal to 1 case. Well, if you set it at k is equal to 1, as I've noted down here, that's pertaining to this diagram, okay, that's going to be too flexible, okay, too much flexibility, which, remember what we mean by the flexibility, high flexibility versus low flexibility. If it's too flexible, well, generally it has low bias. Now remember what we meant by low bias. It means actually for this particular data set, it's not doing too bad, right? Because it's kind of getting out all those intricacies and things like that. So it's not very biased, and that would be analogous to that situation that I keep drawing. There's my regression, right? With 4 points, I say, wow, this is going to be perfect. Connect the dots at home, right? So your son or daughter connects the dots and you say, well, this one connects with this one, this one, this one. Perfect. Describes this particular data set really well. Does an excellent job at it. So it has low bias. This is describing this really well. It's doing a nice job on that. The problem is the method that we're using has high variance. And why does it have high variance? Again, because if you take this on another data set, okay, so try applying this function to another data set, that's probably not what's going to happen, because the next data set's probably going to look like this, and you're going to try to do this again. Well, something like whatever I have there, right? You're going to try to do that again. You're going to try to fit the same functional form to this, and it's just not going to work. It's going to have high variance. The fit is going to be poor. that generalizability is going to be bad. Analogy, what's this situation here? That's the like 2.6 creamers. 2.6 creamers, one sugar associated with the coffee. That's what must be doing it for my client, right? My client is suffering from depressive symptoms and depression, and I think it's related to caffeine, but most specifically, it's related to how many creamers and sugar. Well, maybe for that particular client, you actually have low bias, because maybe for that particular client, they are really sensitive to the creamers and the sugar and the specific amount of caffeine. So if you take that particular theory and you bring it over to the next client, you say, I've got it, it's 2.725 creamers, and you apply it to the next client, well, it's not going to work. Probably has nothing to do with it. So you have to adjust it, right? You have to adjust it. You become a little bit more by increasing k is equal to 100. But with k is equal to 100, it's not sufficiently flexible in this case, okay? So here it kind of does this over here. So you have high bias and you have low variance over here. Okay, so you can adjust your k and n values, but there's a bit of a trade-off when you do it. Now, the trade-off, it isn't always one-to-one as we would think. So look at what the authors did. They did a simulation study here. A lot of these graphs that we're looking at are based on simulated data, because even computing and comparing things to the Bayes decision criteria, like we say, that usually has to be done on simulated data because we don't know those conditional distributions. But look what happens here. This is kind of interesting. If k is equal to 1, okay, so here's k is equal to 1 over here because it's 1 over k is what they're evaluating on the x-axis. So this is 1 over 1 over here. Let's see what happens as k gets larger. So we have the Bayes decision criterion here. Okay, that's the Bayes decision criterion. And let's look as the level of flexibility assessed using 1k increases, or equivalently as the number of neighbors decreases. So what happens as the number of neighbors decreases? So we go from like 1 over 100 over here to 1 over 1 over here. Well, what happens, and what we would expect to kind of see, is the training errors go down. Remember what the training errors are. That's on the data that you have. Okay, that's on the data that you have. That would correspond to this particular situation, k is equal to 1 over here. Low training errors, right? Low training errors. Now, why does that make sense? Because you're actually able to train it really well on your data, right? So the training errors, that's on the data set that you have that you're training. You're teaching your statistical method how to do a good job on that particular client that you're dealing with, right? That's kind of what we're dealing with, right? Or that particular data set, whatever you're dealing with. So you've trained it really well, but as we go this way, the error rate increases. And it makes sense that if you have this situation where k is equal to 1, you have 1 over 1, yeah, the training errors are low because look, it's not making much of an error. But look at the test errors, right? The test errors are actually quite high. And what's interesting here is the test errors, if we go back, so we're increasing k over here. What do we see? We see it actually doesn't like change like in a linear way, because this almost looks like it's linear. It doesn't change like that. It goes like this. It goes down a little bit, and then it goes up until over here you have high error rates for both. So it's kind of interesting that you know, you want to be able to say for a particular situation a larger k is better, a smaller k is better, but you can't really say that. And it's going to be a little bit different depending on the data set. So you might have to try different values of k to see what works best. But you see for that low k, you see that distinction there that we're drawing. over here. So that's a kind of a useful simulation to kind of see those training versus test errors. And remember, what's the goal? The goal isn't to minimize training errors. The goal is to minimize test errors. Carl Rogers, humanistic psychologist, would not care about this graph, right? Because most humanistic psychologists would be most interested in that particular client. So they would say, so long as I'm minimizing the training error, case studies, right? So long as I'm minimizing the training errors, who cares about the test errors? Because I'm not testing that theory on someone else. I'm interested in what this person's going through. I'm interested in all of those kind of chance things, right? All those specifics about that particular person. So I just want to minimize training errors. What about test errors? Who would want to minimize the test errors? Well, that'd probably be somebody like good old Skinner, right? Skinner would say, well, no, I don't really care about this particular rat or this particular pigeon. I care about what pigeons do because I care about the universal kind of laws of behavior, of conditioning and things like that. So they would probably want those test errors to be low. So again, you take this and you compare it to a whole bunch of things. You can compare it to life situations, but in terms of modeling, we want to minimize the test errors because in this approach, taking like a scientific approach where we want generalizability, right? We want some kind of generalizability. And you hear the discussion of COVID again on TV. I was just hearing Dr. Fauci talk yesterday. It is remarkable, and it's not their fault at all, but it is remarkable how little they actually know about the virus. So, when they talk about whether it affects young, whether it affects old, and things like that, they really don't know. So they can look at a particular person and they can say, okay, well, this person has such and such characteristics. I think we've isolated what's important about the virus, right? They have the pre-existing condition, they're like older, etc. And then they find somebody who they try applying that criteria to somebody else, and then they find out it's different. So they're trying to figure out what's going on, and you can compare it to this type of thing. Take the theory based on the training and try applying it to the new data, but your error rate may actually be pretty big. So interesting there. Okay, so that's the KNN approach, and the KNN approach can be useful, and you'll have to do a KNN approach for your next assignment. Some practice trying out that classification method. Weaknesses of the KNN approach. Well, you may have seen that the KNN approach is actually kind of atheoretical, right? It's kind of atheoretical. And if you want to think of it this way, you think of it in terms of the KNN approach is kind of like that black box thing. We're just trying to get the prediction right between the groups. But we're not really studying any kind of function, right? So if you want to know, hey, what's that underlying variable that's actually responsible for the classification? Well, we don't really care about that. We just care about classifying those who will commit bank fraud versus those who don't, and trying to see what our success is. So much for KNN. Let's move to a different method. So what we've just studied is that KNN approach. Now we're back to where we left off last time when we were talking about logistic regression. So we talked about logistic regression, then we stopped, and then we're now moving into linear discriminant analysis. Okay, linear discriminant analysis. And linear discriminant analysis is a competitor. You can think of it as a competitor to logistic regression. It has some similarities to logistic regression, but it goes about things in a different way. So you shouldn't equate the two things. Even though the book does talk about them having some similarities, you definitely don't want to think of LDA as being the same as logistic regression, because they will actually have produce different error rates, produce different classifications many times. So you don't want to think of them as being the same. Well, the first thing, just as we did for the KNN, is to look at Bayes. Bayes features in a lot of these things because ultimately, again, we want to know this. The probability that you're in a particular class, K, given a particular value of X. So if I give you my age, can you predict whether I'm in the COVID yes versus the COVID no? Well, we know Bayes' theorem. Okay, we know Bayes' theorem, and Bayes' theorem is equal to this right side. And there's two components here that are really important. The notation is a little bit weird compared to what we're used to, but this is your prior probability. Okay, this is your prior probability. So in the renditions of Bayes that we've looked at before, this is probability of H. And this whole thing here has been the probability of the data given H. Okay? Sorry, that should be a 1. The probability of the data given H. You can just get rid of that subscript if you want, just say H. Probability of the data given H, probability of H. Now, this is in terms of its density distributions. So for this formula to work, for us to be able to compute this, for us to be able to compute Bayes' theorem here, we need two things. We need Fk at x, so the density at the value of x. What's the density at the value of x? So you can kind of think of this as going, there's x, what's the density at that particular value of x? There, I've drawn a horizontal density. So if you flip this over, you see that density looks like this. What's the density distribution at the particular value of x? This pi, that's not 3.14, the constant, that's that prior probability, as we just said. Okay? So this is what we need to make this work. And what will that give us? That'll give us the probability that you're in a particular class given the value of x. So we can see that just like we know Bayes' theorem already, it's a flip of probabilities. If you supply the formula with probability of the data given H, it's going to give you the probability of H given D. That's the analogy to the Bayes formula that we've looked at. The difference in this formula is it deals with the specific density distributions. So it's a little bit different, but the principle is the same. So the question for us then is how to get this, how to get pi sub k. How do you get the prior, basically? That's what that's saying, is how do you get the prior? Well, in theory, you could set that prior to whatever you want, right? Because we know that Bayes' theorem, prior probabilities could actually reflect subjective probabilities, can actually reflect your personal opinion. So technically you could set that at whatever value you want. Now, you usually don't want to do that. In most cases, you're going to set that at 0.5. So you're going to assume that the chance of being in one class versus another class is equal to 0.5. And that's usually the safe thing. And when you do it in software, it's usually going to just use that by default. However, if you have the random sample, okay, from the population, we can compute the fraction of the training observations that belong to the kth class. So if you have, you know, like 8 out of 10 belong to one class, and 2 out of 10 belong to another class, so maybe 8 out of 10 belong to 1, so this is 8 over 10, and this is 2 over 10, this is 2 over 10, well, you may want to set that at 0.8 over here, okay, 0.8 as your prior, because that class has the most observations. Again, you're thinking about that prior in this sense is almost like being like a base, the base rate, right? So look, I'm trying to predict if you're in the COVID class versus not, given a particular value of X, so given your age or given your symptomology, however way we can specify that. Well, if you're coming from a place that actually, you know, has a lot of COVID in existence, well, that's going to influence my prior, right? That's going to influence my prior. So that's the same idea there. Again, usually we'll just set it at 0.5. So that's not the big problem. We can get numbers for that, and that's not that hard. We can get that. The problem is estimating fk at x. So what does the distribution look like for a particular value of x? So this is what linear discriminant analysis is going to try to look at for us and try to get. If we can get those two things, then we can get pk of x, which is, as we said, the posterior probability that an observation belongs to the kth class. So you can take the probability of kx and you can just replace it for all this, because those are basically going to tell you the same thing. And that's what we want. And then what do? Well, we assign the observation to the class for which the probability is the highest. So you compute the probability for one class, you compute it for another class, and you say, based on this, you have a slight higher chance of having COVID than not, because your probability is highest in that class. Now, this is kind of the ideal again, but we can't get the ideal. You're going to notice that Bayes' theorem is always the ideal, right? But we can't get that. So what we have to do is we have to estimate fk at x. Enter linear discriminant analysis. Okay, so ideal, less than ideal, but let's see if we can estimate these values. Let's see if we can estimate these values so that we can work with it. So again, we're in the idea of like almost like an approximation, right? Well, kind of like the Bayes' theorem would be best, but we don't have that information. So we have to actually do some estimation. And notice that these principles up here, one more note on this, all of this makes good sense. Only if the terms in 410 are all correctly specified, right? So in this equation, only if we can get those terms does this work out. So we're going to use linear discriminant analysis to try to help us out here and help us make that class prediction. So P is equal to 1. You have one predictor. So if you want to draw the function statement, there's y0, 1 based on x. Okay, and for now we're going to consider x to be a continuous predictor. So you got x trying to predict class membership 0, 1, and those are also mutually exclusive as well. So if we can obtain the estimate for fkx, we can plug it into Bayes' theorem in order to estimate that posterior probability, right? Posterior to having looked at the data, right? That's what that means. The probability before is your prior, and then you look at the data, and Bayes' theorem tells you what the posterior is. Again, same logic as we've looked at for things like the probability of HIV, the probability of COVID, and that kind of thing. In order to estimate fkx, we are going to need to make some assumptions about its form. And now this is important in terms of what linear discriminant analysis is about, because we should be able to make some of those assumptions. Well, we're going to assume that that distribution is normal or Gaussian. So Gaussian is normal, and we want to assume that that's normal. Now that may kind of look a little bit familiar, because there's another methodology that you've studied in previous courses where you have to assume normality, right? What did you have to assume normality for? You have to assume normality when you're doing things like t-tests and analysis of variance. So watch this, right? You have one class here, you have another class, and now they're telling you you have to assume that that distribution in here is normal and this distribution is normal. Well, that looks a lot like what you do in a t-test. It looks a lot like what you do in analysis of variance. Okay, now the book isn't telling you this. They're just saying, well, there's discriminant analysis. But I'm helping you see this analogy of what we're actually flipping around here. Because if this is our continuous variable over here, and there's our binary variable, as I mention all the time, I say, statistics can only do so much. Well, what if we moved x over here and y over here? Doesn't that look like the t-test situation? And as we're going to see, discriminant analysis and ANOVA and MANOVA are opposites of one another. And that's coming up in the second half here. So this normal or Gaussian assumption kind of alludes us to that idea that maybe we're doing something very similar. We're just flipping the variables around. Okay? And it is very similar. So what does that mean, the normal or Gaussian? Well, the normal density takes the form of a normal distribution. Okay, so there's the normal distribution. We've all seen the normal distribution before. So the distribution at x, okay, the distribution at x is equal to this. Okay, so it's got a variance, it's got a mean. Mu k, variance k for the kth class. Okay, for the kth class. Again, you have like two classes. There's two classes. So you have to assume normality for that particular class. We're also going to assume something else. Look at this. Variance 1 is equal to variance k. How many classes do we have here? We have 2. But if you had more classes, well, you'd have kth classes. That's why we need the subscript there, 1 to k. So far, we just have variance 1 is equal to variance 2. Now, does that look familiar? Okay, that may look familiar because we have to do that in the t-test as well, right? You have to assume that your variances are equal. So wow, look at how the complexity of where we're at in this like sophisticated like linear discrimination and classification system is all of a sudden looking simpler because it's like, wow, we had to assume that for the t-test too. And again, we're headed here where we see they're opposites of one another. So all of a sudden this starts to look a little bit familiar, saying, yeah, we have to assume variances are equal by the classes. We assume there's a shared variance term across all k classes. What does that sound like? Kind of sounds like that MS error idea, right? It kind of sounds like that pooled variance idea. There's a shared variance across all the k classes. You have to ensure they're equal, and you're kind of thinking about that pooled idea. So what happens here is we plug in this distribution. This is a direct plug-in, okay? So there's nothing kind of mysterious going on here. There's our prior. Plug this in right over here. This is just putting this whole thing here for the fk of x density. Same thing on the bottom. We're just putting that in. So after we plug that in, we can get the posterior probability for the particular class. You can get the posterior probability for the particular class, and you would classify based on which one has that highest probability, as we said. So this is how discriminant analysis is working. And again, we've emphasized this idea that, wow, this might be very similar to the ideas of analysis of variance where we're headed. So I'm kind of giving those clues as we head towards this. Now, this situation here is the situation where we said P is equal to 1. It's the simple case. It's the simple case. Things are going to change when we get to the more complicated case in a moment, but this is only for a single variable. In your book, when some work is done on this formula, you can compute values for the classification that allow you to know which group it goes into. But you can always think about it in terms of the probability of belonging to a particular group. And when we do this classification for the simple situation of only having a single predictor, we look on this side, again with simulated data, there's the Bayes decision boundary, there's the perfect boundary, and this is the decision rule that's going to be computed based on our discriminant analysis over here. So we see that it's actually pretty close to the Bayes decision boundary, but it's a little bit different here. Why is it different? Well, it's different because you're having to estimate parameters. Right? You're having to estimate parameters. We don't know what mu k is. You know, we just don't know what mu of k is. So we have to estimate those parameters. We have to estimate those parameters and get a mu k, right? We have to estimate the parameters for the variances. We don't know what the variance is here. We don't know what this variance is here. We have to estimate parameters for it. Again, that might look a little bit similar, well, maybe a lot similar actually, right, to this. Because if this is the t-test, what did we have to estimate when doing a t-test? We had to estimate means. What was this in the t-test? This was equal to mean 1. And then we had to estimate another mean 2. We had to estimate a variance. There's a variance. There's a variance. We're just looking at this problem from a different perspective where we're doing classification based on that response variable. But you see how the two problems cannot be that different from one another. So the short answer is this, is that when we did a t-test, in a sense, we're also doing a discriminant analysis. We're flipping it around now, and we're looking at some details of what makes that discriminant analysis kind of tick a little bit. Okay? So that's a really strong way of conceptualizing what we're doing here. Well, for the case of p is equal to 1, it's kind of simple, right? It's kind of simple. You plug in your formulas, and you're fine. You can do the classification. But p is equal to 1 is actually pretty easy. And like I say, you can liken it to the t-test idea. You know, you'll reverse it around and think of it as t-test. Everything changes when you consider p is greater than 1. Everything gets more complicated. Now, why does it get complicated? Well, it gets complicated because of one reason, because you have, in this situation, you have covariance. Okay, you have covariance. So we have more than a single variable trying to do the prediction. So you have 0, 1, but you have x1 and you have x2. These two variables now jointly are trying to classify between groups. There's x1 and there's x2. So what it shows here is the multivariate Gaussian density for p is equal to 2. In this case, the predictors are uncorrelated. Now, they'll never be uncorrelated in the sample that you're dealing with. Things get complicated because whereas this used to be the function we're throwing in, well, we have to put in a more complicated function now. And if you look at the univariate, this is the univariate density that we saw up here. Here's the multivariate. Look how similar they are. Okay, there's one crucial difference between them. Look how similar they are. You got x minus the mean, etc. The terms look very similar. But what's the big difference? The big difference is this. Okay? And that's the covariance matrix. So it appears here too. This used to be just the variance, right? You can get away with just the variance, but now you got to deal with the covariance. This -1 we know is the inverse. So you can think of this x minus the mean transpose x minus the mean. Notice that this is in the denominator here, right? 1 over. Variance appears in the denominator. Well, we know in matrix algebra, based on our study of matrices, that we're not putting this in the denominator, we're calculating the inverse instead. So we're taking this, multiplying by the inverse, multiplying by x minus the mean. So in a sense, if you want to think of it, this is appearing in the denominator here. That's the way to think of that inverse. So remember that inverse is kind of that analog to division in matrix algebra, whereas here it appears in the denominator. There's the similarity, but that's where the similarity ends because this is going to be more complicated now. Why? Because instead of just having a variance, you have a covariance matrix. So you have x1, you have x2, you have x1, you have x2. There's x1, x2. So there's my matrix of predictors. Here, what am I going to have? I'm going to have a variance. Here, I'm going to have a variance. Here, I'm going to have a covariance, right? There's that matrix idea of the variance covariance matrix, or just called the covariance matrix. Now, we also take the determinant. Okay, there's the determinant here. Those two bars are indicating the determinant. It's not the absolute value, it's the determinant. Think of what that determinant is accomplishing. Well, the determinant here is taking this variance times this one, which is how we're going to compute determinants. That's how we compute determinants. This one times this one minus this one times this one. Okay, so this variance times this variance minus the product of these covariances. So think of what that determinant is doing. It's accounting for covariability. It's not enough to just take the two variances. You're subtracting out the covariability. In a sense, you're not double dipping, because you may say, look, I've got variance in my distribution, but the determinant's saying, yeah, but we also know you have covariance. You have overlap, right? You got overlap in your Venn diagrams. So let's subtract out that covariance. So again, you can see why that's figuring into this density. So here's an example with three classes over here. Here we have three particular classes. And from each class are drawn from a multivariate Gaussian distribution with p equals 2. So we have two predictors, but we have a three-class problem. And here's what we're trying to predict, our different classes. So we have each particular class has a specific mean vector and a common covariance matrix. Okay, now this is where we start to get into this stuff here, because the mean vector is extremely hard to visualize from this perspective. But just keep that in mind for now, because when we come back after the break, we're going to be talking about mean vectors. But the Gaussian distribution here will assume you have the mean vector and the common covariance matrix. The common covariance matrix is easier to visualize, because you can say, well, I need a covariance matrix for each of my classes, right? I need a covariance matrix of x1, x2 for class 1, for class 2, and in this case, there's another class for class 3, because there's three classes. Okay, so I hope that makes sense in terms of this covariance idea. And everything we've talked about the covariance idea here, that probably makes some sense, right? That we have that. Now that's a parallel to this idea. This idea is equal variances per group. Think of the t-test, equal variances per group. This is equal covariances per group, because you have x1, x2. So these covariance matrices should be equal, should be common per group. Those should be common covariance matrices. Makes sense. What doesn't make sense right now is this idea of a mean vector. And in this book, they slip that in there, right? When you look at that mean vector, say, where's the mean vector? How the heck do we have a mean vector here? Where does that even conceptualize? And this is where we're filling the gaps with this book here to get to MANOVA. But for now, think of the mean vector as what we've talked about over here. There's one mean and there's another mean. That's the lead into it. This is going to become more complicated after the break, but that's what you start by thinking that as. Okay. They don't mention MANOVA. They just mention that mean vector, and we'll fill in the gaps. So here, just to finish this idea here, the dashed lines are the Bayes decision boundaries, and it's a three classification problem. So if you're here on x1, here on x2, well, you're predicted to be in here, et cetera, for the three group problem. So we're into that multivariate. Notice as we go from this kind of univariate idea here to the multivariate, what's the big difference? The big difference is this. We got to deal with the covariability among those predictors, and we have to deal with mean vectors. Really, really crucial. Okay, very quickly, I just want to mention quadratic discriminant analysis. So here we had to assume a common covariance matrix. Quadratic discriminant analysis is another methodology that doesn't assume a common covariance matrix. It doesn't assume it. You can have, each class can have its own covariance matrix. So it doesn't assume that they're common. Now, there's some disadvantages with doing that. So it's going to assume that, for group 1 is not equal to group 2, is not equal to group 3. Whereas the classic discriminant analysis assumes it's common. This is equal over here, assumes it's common. Okay. Equal. So this one assumes it's not. Now, there's some issues with that. You can try it on your data sometimes because maybe the boundary is not a linear boundary, as we see here. So here, the purple dashed line, the LDA is the black dotted line over here, and the green is the solid green. So in one case, you have a linear boundary. So right details are given the left-hand panel, except that the covariance matrices are not equal. Okay, so the purple dash LDA for a 2-class problem with equal, so this is under the condition of equal covariance matrices. This one is a little bit more complicated because it doesn't have this kind of fine shape over here. So here's where maybe QDA might actually be better. Covariance matrix 1 does not equal covariance matrix 2. And since the boundary is nonlinear here, okay, so it's nonlinear, it's better approximated by QDA rather than LDA over here. So it kind of a little bit more of a complicated function. But the problem is when you do QDA, you have to estimate more parameters than in the LDA. So the LDA is kind of a little bit more, it's simpler. If you can get away with just LDA, the linear discriminant analysis, you're usually better off. So you don't want to be trying quadratic discrimination first. You want to try, the linear one, because again, this idea of generalizability to new data sets. If you start fitting too complex of a function, well, maybe it doesn't generalize well to the next data, right? It may have, what are the terms? It may have low bias, but it has maybe a little bit more high variance because maybe the next data set you look at isn't going to have that, complicated boundary. It's going to look more like a linear boundary. Okay. So that's the idea behind quadratic discriminant analysis. So again, sometimes it fits better, and you can compare linear to quadratic on a given data set, and there's nothing wrong with doing that. But what's the big principle here? The principle is that if it's not going to generalize well to the next data set, then just, what I like to say is underfit a little bit. Can you get a pretty good fit using the linear? Then use it. Don't complicate the problem too much because it's not going to be useful theory. Okay, and again, you liken that to scientific theory. They're trying to do that with the COVID, right? They're trying to say, what's the theory? Is who's getting COVID? Well, if they make it too complicated and too much on specifics, and they say, you know what? Our theory, as analogy, is going to be like a QDA theory. It's going to be like complicated. Well, it's not going to generalize well to the next person. They're trying to get the generalities because the generalities can help you make pretty good predictions for the future. And if you get too specific, well, you've predicted well for that particular person, but who cares about that particular person? We don't care about this. We care about the future data. We care about the test data. Okay. So there's discriminant analysis. You have to do discriminant analysis for the assignment. We'll be putting that on the assignment. We've looked at the one part of what we're going to do today. Now, when we come back, take a quick break, come back, we're going to look at what is offered in Stevens, and we're going to call this by the name of multivariate analysis of variance. So we're going to look at this side of the break coming up, we're going to be unpacking the idea of the mean vectors. So there's the relational point. There's mean vectors here. This is what's coming up here. We're going to look at it entirely from the perspective of the mean vectors. And when we come back, you're going to see that this stuff is going to relate directly to this. And you're going to see what they were talking about when they talked about the mean vectors right here. Okay, so I'm going to take a quick break and I'll be right back.